Space stations and space telescopes that we launch from Earth are limited by the size of the fairing for the rocket that they launch in. And, for the longest time, this has been handled by assembling space stations over time with multiple modules, by using origami to compress a space telescope down so it fits within a fairing. But at a certain point, origami will only take us so far, and we want to actually be able to assemble our large structures in space. And my guest today is thinking about exactly how to do that. He's Dr. Vojtech Holub. He's the co-founder and chief innovation officer for Think Orbital. He and his team recently won a NASA NIAC grant to develop a space dock. And so we think about a dry dock here on Earth where you have a ship that's built and then it's moved out into the ocean to continue its way. And you think about science fiction where you've got these spacecraft that are built in this space dock. Imagine that, but for real. And so this idea would involve assembling structures in space, welding parts together in space, and all of the complexity. And Think Orbital has actually done experiments of welding in space for the first time. And so we talk about the welding experiments, we talk about the NASA NIAC grant, and sort of what possible large-scale structures could you build in space. So enjoy this interview with Vojtech Holub. Vojtech, we've got you here to talk about the recent NIAC 2025 win, and we're going to get to that in a second, but I want to sort of set the stage here, which is that you have already done some tests in space with space welding. Can you talk about the experiments that you performed?
Oh, yeah, absolutely. So our company started with the idea of building large structures in space, and that's where the NIAC comes in as a kind of what could we do eventually when successful as a company. But how do we get there? How do we get to building stuff in space? You have to build it from metal. You have to learn how to join metals in space. And we're the only one has done it. So when we started the company, we are super excited about building large structures. But first, it was clear that we have to start building the tools, learn how to weld, cut, and potentially X-ray inspect the welds in space. And starting with the welding, we designed an electron beam welder that can works with 20,000 volts that can penetrate roughly quarter-inch aluminum in a single pass. So most of the space structures are more than good enough. And we designed it. We managed to convince SpaceX to let us launch it. We designed kind of two welded canisters, one where you actually weld it and one that contained all the electronics and avionics in a pressurized state, so we can keep it simple, not really vacuum rate anything. And yeah, we launched on Falcon 9 on the 6th of May. We welded while kind of on top of the parabolic flight at roughly 120 kilometers altitude. We welded roughly for 40 seconds, landed, got the payload back.
Oh, that's great. Okay, so you actually did recover
Yes.
the payload. And how was the weld?
No one really prepares you what the environment in the interstage looks like. So we did weld, but we had issues with the motor that spins the sample underneath the welder. Because as the second stage lit up, it melted some mesh screens that SpaceX forced us to put on in order, to prevent any potential loose bolt or anything coming out of the payload. So we managed a bunch of spot welds because of the motor instead of actual welds, but the system worked as designed. And what was kind of surprising and shows the state of the startup, we have this awesome first weld payload that in 40 years no one welded in space. And we just plugged it into vacuum chamber here that we have in-house and run more experiments with it. So it survived the flight.
So, I mean, that's exciting, right? Like, we talk about this idea of assembling large structures in space and about how we're going to be mining asteroids and using that material for building things in space. But like when it comes right down to it, you need to be able to weld this stuff together. And a lot of people are familiar with some of the challenges of welding in space. I've heard this idea, there's this idea of cold welding that you have this problem with metal that just touches and starts to weld together. So like what, before you even went into this, what is just sort of your understanding of how attempting to weld something in space is different from how we weld here on Earth?
So on Earth, most of the welding is done through arcing through gases, which produces a lot of heat. That's very difficult to do in space. Likely doable, but if you want to weld in space, you don't want to carry canisters of gas that you just dump. That's inefficient and a lot of mass. So that leaves you with roughly two options. One is laser welding, which just requires electricity. And then there is the electron beam welding, which we are using. And also in 60s, the experiments done by 60s, 70s, Soviet Union did a bunch of experiments with welding, and all of it was electron beam. The reason why we went with electron beam instead of laser is just efficiency and penetration. It's if you had a long checklist of everything that you want your space welding to be, the electron beam welding pretty much checks all of it. Like, it's done on Earth quite regularly, but mostly in specialized cases like welding nuclear cores or thrust chambers of rocket engines, because it requires vacuum to operate in. So that makes it very kind of slow and costly, not very prone to mass production. But all you need is, in our case, 2 kilowatts of power. So like your iron, pretty much, or electric kettle. And you can weld 1 centimeter per second of 1/4-inch aluminum. So very fast, very efficiently, because it's such a narrow beam, your heat affected zone is super small. That results also in high quality, strong welds, not much, heat that ruins the structure of the metal.
And give me a sense, like I did welding in high school with oxyacetylene, and I've been around when people have been doing arc welding, but give me a sense of like what the finished product would be like if you had to, and I've got a bike made of aluminum, so I'm familiar with what the welds look like on my aluminum bike. This is great. You're actually holding up.
Focus.
So is that the actual weld that went to space?
No, this is from the before flight. This is the testing that we did.
Okay. All right.
So it doesn't look that different. You have the entry point, exit point, you have nice bead in the middle. But since I'm showing stuff, electron beam gun, electron beam welder is a little bit like your old school CRT TV, which also, projects beam towards the screen, and then you have coils quickly rasterizing. And you can raster with electron beam welding too. And when you do it in a smart way, you can achieve, when I was talking about electron beam cutting, come on.
So for the podcast listeners, he is showing some really cool welded metal.
And this is cut metal. You can scalp the metal away to create clean cut, which produces no debris, but more importantly, no thrust. So you don't need fixturing away.
Yeah. Oh, that's amazing. So then let's sort of then talk about your proposal for NIAC. So, and this is a phase 1. So often this is very much about you have an idea that you want to develop further. You want to sort of explore the feasibility of the concept. And so what idea are you proposing to NASA?
Yeah, so NIAC is a little bit of a special vehicle, very different from anything else that NASA does. Most of the funding goes to like phase 1, phase 2 SBIRs normally that are very specific. Like it has to be in NASA's roadmap, and we need this specific thing to make it work. NIAC is very much future-facing and far future-facing. We actually submitted something like 2 years ago, which was the assembly of the space station, roughly 3 times, 4 times the size of the ISS, kind of similar concept. And it was not deemed futuristic enough for NIAC in the reviews.
I love that. Not futuristic enough.
So this time we decided, okay, let's bring it to the next step. What could we do that would help humanity in case we can achieve it? And before going fully to like O'Neill cylinders, we thought of space dock. Like, if you want to really explore with human solar system, you kind of need to get away from restricting your vehicles to something that can be launched, something that can survive shock and vibe of the launch environment, something that has to fit into the payload thing of a rocket. So you would want to build in space. How would you do that? How do you do this with ships on Earth? You have dry docks. So the idea was, could we design a dry dock that you could build potential space vehicles in? And all boils down to kind of a pre-assembled pieces on Earth, flat-packed as IKEA style, put into the rocket, and then assembled and welded in space. So that's where the welding comes in. And that was kind of the original idea behind the founding of the company, but it was much more kind of a realistic, not realistic, but smaller scale to start with, pressurized volumes that are, let's say, 2,000 or 4,000 cubic square meters, so 2 to 4 times the ISS volume.
Wow. Wow. And I sort of imagine Star Trek, where they have these scenes where they're approaching Stardock, and there's this, the new version of the Enterprise is sitting in this space dock, and they sort of fly around it and examine it as it's being constructed, and people are on the outside of the spacecraft and they're welding components together. It's sort of exactly the version of a dry dock, but now it's out in space. So how would your space dock compare to the science fiction version or the land-based version?
Yeah, no, seriously, the science fiction vision, like you watch any space show, and you don't see a bunch of joint cylinders flying around. It's always a large structure that explores the space. So with respect to them, kind of in the NIAC part, we have multiple versions. Some is for kind of building starship-sized vehicle. Some is for up to, and as a popular picture there, up to Imperial Star Destroyer, figuring out what would it take, how many launches, what's the cost. So part of the NIAC is actually to figure out how to convert it to real numbers, and what would the concept of operation be, and how would the humans live there, or would it be mostly automated? Would it be human welded in just oxygen masks or something? So the point of the NIAC, I think, is to show the scalability and show that whatever you do in this way in space, you need to be able to assemble. You need to be able to launch not fully assembled vehicles and put them together in space. And once you manage that, the opportunities are infinite. If you want a very large radio antenna, you can do that. If you want a very, very long beam for your solar arrays that you can weld in space, you can do that. And the NIAC is part of it. If you can have a lot of prefabricated pieces and weld them together into large structures, this is what it would take. So that's the investigation that we would be working on.
Now, you sent me a paper that you had done about this mission called Orb 2. And this was very much in that same vein. And you sort of showed this example of a New Glenn capsule containing sort of the central bus, but then also just these plates that are stacked up nicely and compactly that could then be assembled in space. So talk us through sort of that example as a more concrete type of thing. And you're saying that like this was not futuristic enough.
Exactly. And it's interesting because when you see that, it's kind of obvious, like this makes sense. So imagine that your goal is to assemble a large pressurized volume. What's the best shape to do it from mass and engineering perspective? Sphere. That's what allows you to have uniform stress distributions and the lowest mass for highest volume and so on. So how do you build a sphere? You could divide it in a similar way how you divide a soccer ball. There is the whole family of shapes similar to the truncated icosahedron that a soccer ball is mathematically called. But then you want to divide it into certain amount of parts that would well fit into the payload fairing of a rocket. So that's why that specifically one was the soccer ball kind of division of shapes, because it fits well into the diameter of, at the time, New Glenn. And
it was like, if I remember, like it was a bunch of, like a soccer ball is a bunch of hexagons and a bunch of pentagons. And so you would have a stack of pentagons, you'd have a stack of hexagons stacked up underneath this main hub. And then once in space, it would start to grab the bits and pieces and start to assemble this into a sphere in orbit.
Yeah, so you would have eventually, so you want to build a large volume in space, but initially it's going to be an empty space that can be pressurized, but it's an empty space. That empty space doesn't make a space station. You need some sort of a service module with all the attitude controls and docking ports and solar arrays and radiators. So on top of this stack of flat-packed future segments that will form the future volume, we have the service module that contains all this stuff. Very similar to, for example, what for the Lunar Gateway, the service module would be.
And so what kind of internal volume would you be able to get with that, fitting inside the fairing of a New Glenn?
For single launch in New Glenn, it would be 2,000 cubic meters. If you scale it up to Starship, it would be roughly 4,000 cubic meters. But if you go away from the requirement to put it up in a single launch, it's pretty much unlimited. Of course, the physics dictates the larger it gets, eventually you need much thicker walls. But again, once you have the assembly method, which is a robotic arm or multiple robotic arms moving these pieces around, aligning them so they can be latched on the side of the panels, and then welded together, you can build any size pretty much.
And so let's talk about those, like the pressure is an issue. And people have been exploring inflated habitats, and there's some really interesting, I think they work surprisingly well. What do you find is sort of the size, the thickness of the metal, the thickness of the welds compared to the volume that you can hope to expect and still be able to pressurize it so that people can be in there?
So on the first part, I think inflatables are kind of a step in the right direction, but it doesn't get you all the way because the ratio that you can inflate with is not that high. It's maybe 3-to-1, maybe 4-to-1. But so in theory, you can expand to 3 times, 4 times the size of the payload fairing. But that's about it. Great step in the right direction. And on the second part, I think most of the people would be surprised how thin the actual walls of the space station are. On space station, the actual thing that holds the air in is roughly between 3 and 4.8 millimeters thick.
Wow.
So, and interestingly enough, the reason is not pressure. For pressure itself, mathematically, we need like 1 millimeter. But it's for protection from micrometeorites and orbital debris, mostly. So similar with the what we are proposing, the assembly method, the initial limitations is protection from micrometeorites and orbital debris, and you would have to start getting very large to need to increase the thickness for pressure reasons.
If that's the case, then you're looking at aluminum, sheets of aluminum that are a couple of millimeters thick, and that you are then pulling these out very carefully, because it sounds like they actually be very delicate to then start to weld them together. It's almost like at a certain point you want them to be a little thicker just to be able to handle the rigors of the weld and the moving them around back and forth, the tensile strength.
Right, and that's why we kind of designed the welder to do 1/4 inch, so you have a little bit of margin. So if you design such a piece, it would be kind of your typical space isogrid, kind of a spin-formed machined isogrid with thicker edges. So if the weld reduces the strength of the metal by 60% or so you have the margins there. But again, the pressure, at least in the sizes that you can fit into a single rocket, including Starship right now, the strength is like the thickness is driven by the protection from micrometeorites and orbital debris, not really the stresses of the pressurized vessel.
And so then, if you do scale up the actual sphere that you're building, you showed an example where it looks like there was thousands of panels. Then you're making it thicker to protect it from orbital debris. What's like a thickness where it starts to feel very safe and also is holding a large volume? Like how big can we? What's the sweet spot, do you think? If money was no object, to just like launch as much of these panels up as you wanted and assemble them together in something that feels very durable, very strong, and very protective, how big would you want one of these things to be?
So there is a use cases for building structures like this that is not pressurized. For example, if the space is not pressurized, then you still have protection from radiation added, protection from micrometeorites and orbital debris. You don't go through the thermal cycles that you would normally do. And so the majority of the dry dock for the NIAC would not be pressurized because it would be very difficult, especially kind of you would really have to go in kind of the spherical shape. But if you release the requirement for pressurization, you can just build a cube or something like that, and you can have a big payload door open and have all the nice science fiction stuff. It would have to require some pressurized spaces for the potential crew. But when it comes to kind of, again, starting with the International Space Station, majority of the micrometeorite and orbital debris shielding, the whole sandwich is, let's call it 4 to 5 inches thick. And it's using something called Whipple stuffed shield. So Whipple shield, let's say that you put a thin piece of metal far away from your actual pressure vessel. What happens when a bolt hits it? It doesn't stop the bolt. but the energy release is so large that it fragments the bolt into many pieces, and instead of a single hit into your pressure vessel, it will be like a cone of debris spread out over a large area, and then the pressure vessel can hold it. Now, the stuff shielding is you have some layers of Kevlar and Nexel in between kind of the ballistic materials to make it even better. But the thickness, no matter how large you get, when it comes to protection from micrometeorites, you want to be 5 inches thick as a sandwich. And potentially, there is no reason why this could not be designed in a way that expands one way or another. So you can have it really flat packed and then just spring it out to have the good offset between the pressure vessel and the Whipple shield.
Right, but I'm imagining like if you've actually got 5 inches, that's like 15, 20 centimeters of thickness. I mean, that's starting to protect you from radiation as well when you're inside that facility. So is there, again, is there a sweet spot where you've got maximum protection from radiation, you're able to pressurize it so people can live inside, you've got a nice, strong structure that's able to handle, temperature changes, and you've got some give for the amount of welding that you're doing, is this thing a kilometer across? Like how big? I'm trying to imagine how big this thing gets.
Yeah, the Whipple shield is mostly vacuum, right? It's just a space in between. I think the radiation is a hard one to tackle. We are designing for low Earth orbit where we are still mostly protected with minimum. If we want to go into deep space, I think there is a lot of science that we would have to do in math because sometimes it's better when it comes to like high energy particles. Sometimes you want to be less protected than more because sometimes the particle gets slowed down and breaks out to many high energy particles, which is worse than single one. So I don't have an answer.
Like I know we need a meter of water.
Yeah.
Like a meter of water gets you pretty good protection from cosmic radiation and solar radiation. So, all right. So I'm imagining spacecraft with sort of two shells, maybe a inner pressurized area and then an outer area that is sort of keeping a meter weight layer of water in between that's protecting you from radiation, and then it's got some kind of propulsion system and it's able to then travel around the solar system. This really is starting.
I mean, that makes a lot of sense. You need water for multiple things, including producing the rocket fuel if you have big solar arrays. So
yeah,
you have to store it somewhere.
Into Star Trek. Yeah, yeah. Or maybe that's one of the balls on the back of the Imperial Star Destroyer, right? And then, that's how they all started, is those little balls on the back of them. I think we've learned, like, a lot of the International Space Station was built by humans, astronauts going out on these spacewalks, and they're actually doing all this assembly and overseeing it. But they're also operating the Canadarm and stuff to actually try and bring this together. How much of this do you think could just be fully automated, or how much do you think requires human supervision?
I think quite a lot, actually, because like comparing to catching a free-floating spacecraft in space by a robotic arm, that's kind of a non-deterministic problem. You need a lot of, you don't know where the spacecraft is ahead of the time. You need to adjust real time, grab it. While assembly, you have everything is fixed in its three-dimensional space, where each panel will be at all times. Nothing is floating. So with this respect, I think it's simpler than actually catching a spacecraft. Also, the dynamic requirements on the arm are lower because nothing is floating. You don't have to catch anything at speed. So majority of it, like really, the way I foresee it in the future is that eventually it's fully automated, but initially all you need to do is robotic arm to do its job, get close enough, and then someone in control room just approves you're in the right spot, you're good to go. And then it does, let's call it 10% human involvement, just approving risky operations and making sure that the arm is positioned right.
So you also mentioned in your paper the possibility of starting to generate artificial gravity with these orbs, that you would connect a bunch of them into a big ring or something. How would you think you could actually get something that could provide artificial gravity?
It's quite easy to produce the gravity, right? You just need two orbs connected by a rope. But then it's impossible to dock with such a spacecraft. So I think the real challenge really becomes how do you design a system that has a docking ports and certain things in the center of gravity that you can dock to. So the simplest way really is having ability to spin and despin it, and have just either you build orb large enough so if you spin it around its axis, then it produces some sort of a gravity, which I could imagine like on the ring part that spins of the sphere. You could have like accommodations for sleeping, so at least you sleep in certain low level of gravity, like Mars gravity or lunar, that would help health-wise the astronauts. And I don't think that's that challenging. And if you want the whole thing to be under gravity, you just need to have two opposing ends, habitable or counterweight and a habitable sphere connected by a rope and spin it. I think that's one of the developments. The question is, comes to business perspective, right? We want to go to space to do things that we cannot do on Earth. The gravity really comes into play when you have very long-term human missions. Otherwise, the no gravity is preferred.
I mean, even with one sphere that was large enough and you started to spin it, then you would get gravity right at the equator of where this thing was spinning, and yet you'd have less and less gravity as you move towards the poles, and eventually it would be weightlessness up at the top of the poles. But also, if it was turning slow enough, you could imagine your spacecraft could dock at the poles and it'd be turning as it was doing so, and then you could have people come out and they could float inside, and eventually they would sort of drift and have higher gravity and sort of gently attach. So I'll bet even with just one, you could start to play around with some of those ideas and at least perform some experiments. I mean, there's so much we don't know about providing artificial gravity in space. That
I can imagine that even if you do like a lunar 1/6 of gravity, it makes everything so much simpler to live and work. And that's our goal eventually, to help to build infrastructure in space that allows regular people to do it as a job, pretty much.
Yeah, it's fascinating. So what is your deliverable? What are you expected to provide to NASA for this first Phase 1 NIAC grant?
For the NIAC, the deliverables are to kind of do the concepts of operations. How would you assemble it? How many launches would it take? What's the kind of the mass, and some basic structural math on would it hold together? And that's pretty much it, and potentially do it for multiple versions.
That's cool. So what are you obsessed with right now?
So as a company, so I'm always obsessed with the mission, which is I want to see humanity prosper in space and living there. Now, I'm obsessed with the pathway. How do we get there? And for me, that is kind of what was really interesting is when we talk to people, especially, government, about, well, look at it, we can weld and cut and X-ray. They were very interested in the X-ray part. So that's one of the things that we kind of, as a company, do as a second product. The first product is a toolkit. Think of it as a Swiss Army knife, where you have a box with a robotic arm and an end effector with the gun that you can attach to any spacecraft or any tug. And suddenly a refueling tug is converted into a servicing space tug that you can weld, cut, and if something goes wrong on a satellite, you can get close to it and X-ray whether some mechanical part broke or what went wrong. So that's kind of the first product, and the second one is purely higher energy X-ray of the satellite. So that's kind of the part that's really interesting, and there's a lot of demand in that potentially.
Right. And I mean, that whole part, like being able to X-ray the satellite, being able to determine if there's any flaws, any issues with the welds that you've done, or with just the build of the spacecraft while it's in space and actually handling, like that's a really key part before they begin operations with the spacecraft.
And yeah, there's multiple dimensions to it. So, everyone's talking about how ISS is aging, but do you have any proof? Do you have any X-rays of microstructures that are, cracking or something like that? No, but if you build a tool, definitely you can get a lot of useful information there.
Yeah, that's interesting. I know I talked to somebody about this, just the process of, you do a weld, you X-ray the weld, it tells you whether the weld will meet your standards. Yeah. And if not, then you can redo the weld. But it's good to know, and so that ability to scan inside is going to be key.
It's actually an industrial standard. I think you have to X-ray, like when it comes to pressure vessels, you have to X-ray 10% of the welds at least.
Yeah, I think I was talking to somebody about pipelines Maybe that was it. Yeah, yeah. Awesome. Well, it's fascinating work. Good luck with the NIAC grant, and hopefully you get through this and you move on to phase 2 and you actually build giant Imperial Star Destroyers. I think that's how phase 2 works. Yeah, yeah. Thanks for your time. Good luck.
Thank you, Fraser.
I hope you enjoyed the interview with Dr. Vojtech Holub. Now, we've got a whole bunch of NASA NIAC Grant 2025 winners coming your way in interviews very soon. We'll talk about that a little bit more, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew Gross, Bear Lake Roofing, David Gilton, David Matz, Dennis Alberti, Dustin Cable, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Paul Robach, Sean Sargent, SpiderSwap.io, Stephen Fowler Munley, and Vlad Shiplin, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So the 2025 NASA NIAC grants are out, and there's about 15 different winners, and I have reached out to every single one of them, and I have organized interviews with many of them already, and there's going to be a lot more coming out. And so we're going to put this all into a big playlist, and if you want to think about these really cool futuristic ideas for what we could do in space in terms of science, in terms of space exploration, construction, in situ resource utilization. We've got a lot of really cool ideas. And we've actually done interviews with recipient winners in the past as well. So I'm going to link to a couple of playlists where you can go and look at past winners and sort of see some of the really cool ideas. All right, we'll see you for the next interview.